Hi, I'm Mike Zelinski. I'm a research scientist here at Lawrence Livermore National Lab. I specialize in remote sensing technology. The topic I'm presenting on today is a methane gas leak detection technique, which I believe has good commercial value when applied to finding leaks coming from pipelines. I developed this pitch through the Lawrence Livermore National Lab Accelerator program, along with two outside collaborators, Chris Dombrowski and Donald Price. Leak detection is a multi-billion-dollar industry, and we believe that this approach is an extremely cost-effective method for finding leaks. There's a number of reasons that this work is important. Methane is an extremely potent greenhouse gas, and the amount of anthropogenically released methane in our atmosphere continues to grow at worrisome rates. There's also strong economic reasons for curbing these leaks, as leaks account for nearly $30 billion of lost revenue globally. The U.S. Environmental Defense Fund claims that the oil and gas industry leaks about $2.6 billion a year. There's also regulation. State and federal regulation currently exists that requires pipelines to be monitored. Aerial surveillance is listed as a monitoring method. There's also been a recent multi-billion-dollar lawsuits here in California involving methane gas leaks. This is enough to incentivize companies to look for leaks in populated areas. And lastly, the large financial institutions that have invested in the methane gas industry are becoming increasingly aware of these risks. They want to see solutions, and they want gas companies proactively addressing these issues. Leaking transmission lines only account for about 20% of the leaked methane, which is about $500 million of lost revenue per year. However, they carry a non-obvious importance, which is that transmission lines act like a bottleneck for the entire industry. This is really one of the key take-homes of this talk. To an oil and gas company, shutting down a pipeline means you're shutting down your source of revenue. Every hour, millions of dollars of gas will pass through a single transmission line, and it is therefore critical to keep that line open and flowing, and in many cases this cannot happen if there are leaks. Finding a leak when it is small is often a good thing because it might actually be repaired without shutting down the line. And larger leaks need to be found because when a gas line is operating at 1,000 psi, even a pinhead-sized leak can release millions of dollars of gas. Besides this, it is also important to note that this is vulnerable infrastructure. As can be seen on the map, in many heavily populated areas, such as Las Vegas, there are millions of people who rely on a single natural gas line. Oil and gas production sites leak more regularly, and they're a larger market. But a leak on a single oil well does not carry the same importance to the industry as a leak on a pipeline. The specific technology we are investigating is shortwave infrared hyperspectral imaging. I learned about this field in graduate school, and when I came to Lawrence Livermore, I was able to get years of hands-on experience working with airborne hyperspectral imaging systems. I was primarily involved in writing algorithms for processing the data, simulating the performance of proposed designs, and fielding the sensors themselves. To summarize the technology, infrared light emitted by the sun passes through our atmosphere and reflects off the Earth. If this light passes through a cloud of methane, the gas will absorb some of this light at specific wavelengths. You can think of this process like someone leaving a fingerprint at a crime scene. This imprinted absorbance pattern is a unique identifier to the methane gas. This light is then recorded by a hyperspectral sensor and reassembled into a series of images. Each image represents an individual wavelength of light. You can kind of think of it like a stack of cards, where each card represents a wavelength. Each pixel in the hyperspectral image contains a measurement of the spectrum within its field of view. This is one of the many great powers of hyperspectral imaging. You can actually use a single pixel to find a cloud of methane. and I'll provide a demonstration of that in a moment. As I became more interested in this problem, I was connected to a partner who had an airplane and also offered to help, SkyCam Aviation. SkyCam Aviation is a perfect partner for this work. SkyCam is a new company that specializes in high-resolution imagery of long linear structures like railroads, highways, and pipelines. I'm not the first person to use hyperspectral imaging to find methane gas leaks. The scientists at NASA's Jet Propulsion Labs have been doing this for over a decade. And I determined there was likely a commercially available system that would fit in a single engine aircraft and have the required capabilities. The team at SkyCam was able to connect with the Norwegian maker of hyperspectral sensors, HySpex, and they were happy to receive HySpex's participation on a data collection campaign that covered several regions around Northern California. Here in Livermore, SkyCam Aviation was able to set up an experiment by making a methane bubble using a simple frame and some sheets of plastic. Here you can see 4 plastic cubes. There are 2 with a 6-inch height or path length and 2 with a 39-inch height. Using these 4 targets, they were able to conduct a simple blind test where from each pair, 1 cube was left as a control while the other was filled with methane. This is the part of the talk where viewers who have not seen raw hyperspectral imagery might struggle. A hyperspectral camera operates a bit like a photocopier. The field of view is scanned or push-broomed across the area it is imaging. However, unlike a photocopier, airborne systems experience turbulence, which results in an equally turbulent image. Here you can see a residential area of Livermore. Roads, houses, and cars are visible, but notice that the roads aren't straight. This is a portion of a much larger image, which I can now transition to the rest of that image. At the left-hand side of the image, you'll see a residential neighborhood. Middle left is a commercial area. Then there's the Livermore sewage treatment plant. Finally, on the right is Livermore Airport with several large hangars visible, and the field with the gas cubes in it is on the far right. I'll highlight the areas that have the gas targets with a red box. Of course, the gas targets are too small to make out in these images, so I'll also provide a zoomed-in view. The image on the right shows a thresholded detection image. The white pixels indicate detections on the targets containing methane. This detection mask can then be overlaid on the context image shown on the left, and they're color-coded red. This data was collected from 1,500 feet above the ground, and each gas cube produces 4 pixels occupying a 2x2 area. This result was reproduced several times at Livermore, and I should note it was also reproduced again at a different location in Goleta, California, with the help of a colleague at the Special Technologies Lab who has a similar gas cube that was filled with methane. The Livermore sewage treatment plant is also a source of methane gas. It's typically burned in a flare stack. However, due to incomplete combustion, there is still a substantial fraction of methane that is released. Another location near Livermore that produces methane is the Altamont landfill. Similarly, they collect methane from within the landfill and burn it in a flare stack. We were able to detect a methane plume there as well. Our primary airborne competitor is Lassen. They use a dipole LiDAR, and their technology is highly sensitive and can be operated in low light. But this technology requires lower elevation flights and is therefore less safe. The data is collected at half the speed you would fly a HySpex sensor at, so it is less agile. And because the system is flown in a helicopter, it is much more expensive. Our other primary competitor is Picaro. The Picaro sensor is a point sensor similar to a smoke alarm, It is definitely the most sensitive out of any of the technologies used here, but it is expensive and it can't provide much spatial context. Both of these technologies are currently being used to find leaks. This chart summarizes the sensors used by different competing technologies. I don't have specific numbers I can pin to the competing costs or sensitivities, so for this chart I just keep it general. Two sensors I didn't mention on this previous slides were the European Space Agency's Cyatome sensor, which is a very low resolution imaging satellite, and the mass balancing sensors currently used by the pipeline industry known as SCADA. It is important to mention methane gas leaks come in a variety of forms, and there isn't one technology that is best suited for all types of leaks. For leaks that exceed our sensitivity thresholds, we believe our approach is the safest and most cost-effective way to find them. I should also say that this would be a challenging task for drones given the relatively short flight times, line of sight constraints, and the sheer number of miles that need to be flown. To conclude, transmission line gas releases are a growing issue. The current persistent monitoring technique, SCADA, used by the pipeline owners has a relatively high false alarm rate, which can end up leading to costly inspections. External leak detection technology, like LASSON, is sensitive, but it is expensive and therefore used at an infrequent rate. We want to use a fleet of aircraft with HySpex sensors to image 300,000 miles of pipeline across the US at an affordable rate. This will be done with a simultaneous collection of high-resolution RGB context imagery, which will provide pipeline operators with an outstanding value for the airborne surveillance they are already paying for. This is a business that could operate as a service, providing a set number of flyovers per defined amount of time. Our team has some great talent. Chris Dombrowski is the current CTO of SkyCam Aviation. Chris has a PhD in astronomy and is the former CTO of Aviation. They're an airborne imaging company that focuses on agricultural remote sensing. Chris is experienced in image science, optics, and the aviation business. Donald Price is an energy systems analyst and remote sensing consultant. Donald has spent nearly four decades at PG&E as a senior scientist and worked at Lawrence Livermore for 6 years. Donald has intimate knowledge of the gas pipeline industry and has led efforts in new leak detection technology. I'd like to thank Donald and Chris for their outstanding input and interest in this work. I'd also like to thank Roger Warney and Hannah Farquhar for founding the National Lab Accelerator Program and providing me with some terrific mentorship. Thank you.